Welcome to this video on partial fractions decomposition. Type 3, I call a type 3 problem one that has a linear numerator raised to a power. So, how do you deal with this situation? Well, you break it up into one fraction leading up to the highest power that you have in the denominator. So since our denominator of the original problem is a linear factor cubed, I'm going to break this up into three fractions, each of having a different power of x plus 1 in the denominator. The numerators, p, d, and f, are still constants in this circumstance. The goal here is to find the values of p, d, and f. By writing this second line, we are saying that there is some number p, some number d, and some number f for which these two expressions are equivalent. It's our job to find those. The best way to find them is to condense this back into a single fraction, so I will use the common denominator trick or the multiplying by 1 trick here in this particular case. If you look at all three denominators, you'll notice all three of them equal x plus 1 to the third power. And now that I have created a common denominator, I should, as usual, combine the numerators. The first numerator here is probably worth examining a little bit more closely. It came from the first fraction. It came from the fraction multiplication above it, where I had to do p times x plus 1 quantity squared. It's worth noting a couple things here. First of all, I cannot distribute the p into something that has an exponent. That would be a violation of the order of operations because exponents come before multiplication. In regard to the exponent, I can't distribute an exponent because exponents don't distribute, so the only way to handle the x plus 1 quantity squared is to use FOIL, which I've done here. After doing FOIL, I can then distribute the p, giving me this, and that explains the first numerator above. Now that I have a common denominator, I'm ready to proceed by combining all my numerator terms together. And notice when I put them all together, I slightly rearrange the order. Look at the bottom numerator, and you'll notice I have an x squared term first, followed by two x terms, followed by three terms that don't have an x in them at all. Those are the constants. But remember, the whole goal here is to find what values of p, d, and f will make all of these expressions, and most notably the two in black here, equivalent to one another. Now, how could these two expressions be equivalent? Well, first of all, their denominators are the same, so therefore their numerators must be the same. But the only way the numerators can be the same is if the x squared terms are the same, first of all. And since there's only one x squared term in each, the only way these expressions could be equivalent is if p were equal to 2. Well, that's my first equation of note. But that's not the only thing needed to make these expressions equivalent. The other thing is that the x terms on the bottom would have to add up to 5x, the x term on the top. Therefore, it must be true that the sum of those coefficients is 5. That's my second equation worth noting. And finally, as a requirement for these expressions to be equal, the constant terms on the bottom, p plus d plus f, would have to add up to -1. And that makes my third equation. And now I have a system of equations to solve. And while I'm not going to show the algebra visually, you could almost do this problem in your head. After all, we've already discovered that p equals 2. And if p equals 2, we could plug that into the equation below it. A little algebra will show that d ends up being 1. And knowing the values of p and d allow me to go to the third and bottom equation and solve for f. It's very simple algebra I won't show here, but it turns out that f is -4. Let's take a moment to pause here and think what it is that we just discovered. we discovered that if P is 2, D is 1, and F is -4, all of the expressions on this page are equivalent, and most notably the top two. And if those expressions are equivalent, when P, D, and F are these numbers, watch the second line here, I can replace P, D, and F with those numbers, and I now have equivalent expressions, and I've therefore decomposed the original fraction into the sum of 3, hence completing the problem. Thank you so much for watching this video.